Good day, I'm Dr. T and welcome to my desktop. So today I would like to talk a little bit about the graphs that we typically use when we are presenting data in the harder sciences. Every discipline has its own ways of representing data because it has its own needs, etc. And each individual researcher, each individual paper will do what's best for that one. However, there's a couple of very standard approaches for making graphs. And I kind of want to share those standard approaches with you all. Now, the first one I have up here is a classic XY scatter plot. So in the XY scatter plot, and be clear, this is not a line graph. There are some subtle differences between the two. It does look like a line graph, but if you try doing a line graph in Excel, it's not going to quite come out the way you want it. You want the XY scatter plot. And so with the XY scatter plot, what we're going to have is over here, we're going to have our independent variable. Now, kind of definition of terms. Independent variable is going to be the variable that you control. So, if I'm adding water and I'm looking at plant growth, then the amount of water that I add is the independent variable. If I'm measuring something over time, then the time would be the independent variable. It's the one that's being controlled and that is then affecting the other variable you're measuring. The other variable is your dependent variable. So, in the case of the plant growth, it might be the plant growth. So the water would be the independent, and then the water affects how well the plant grows, and so the plant growth would be the dependent variable. So typically in most sciences, we put the independent variable on the x-axis and we put the dependent variable on the y-axis. I do know that there are some of the social sciences that do switch that. I believe, I'm not positive on that. But typically for the hard sciences, independent on the x. Okay, now you'll notice a couple of things. One, I've got several trials going on over here. Now these are just completely made up numbers, total nonsense. But I've got my independent variable. This would be something I control. And these would reasonably be expected to be clean, just straight up numbers because I measured out maybe 1 milliliter or whatever. And when you're doing this, Excel does not like you putting the units in with the numbers. It just gets confused. So what I would probably have is, volume of water, parentheses, milliliters up here or something. And that would correspond to my title. So I put my units in my titles of, the chart and of the graph. I wouldn't try and put them with the numbers because that will confuse Excel. Anyways, so what I've done is I've measured out my 1 milliliter of water or whatever, and I would have done that on multiple different plants or multiple different experiments. You want replication. This really allows you to see how well things are doing, how much noise you have, how much weird stuff you've got going on. And so what I would want to do is honestly at least 3. 3 is usually considered the minimum. It's the smallest amount you can do a Q-test on, which is going to allow you to throw out data if it's an outlier. So if you've got data you don't like, you can't just chuck it. If you know why it's wrong, like you drop the plant or something, then you can throw that out because it's bad data. You know why it's bad. It's just bad. But you can't just throw it out because you don't like it. That's called cherry picking, and that is really bad. It's a great way of creating a false narrative and allows your personal biases to impact your research, which is not something you want to happen. So you can't just throw it out. But one approach you can is if it really is off, you can use what's known as a Q-test, and that Q-test can indicate that it is statistically not appropriate data. The smallest number of data points you can do a Q-test on is 3. More is always better. Anyways, so I'm going to do 3 trials, and then I'm just going to do an average, add them up, divide by the number of trials. And then the next one I want to do is a standard deviation. You'll notice on the screen the formulas that Excel is using to calculate these. Standard deviation is looking at a statistical representative. Standard deviation is looking at a statistical analysis of how those data points align and how close they are to each other. The smaller your standard deviation, the tighter your range is, the less diffuse they are. If you were to do a bell curve, it would be a pointier bell curve, whereas a greater standard deviation would be a wider, more spread out bell curve. And this gives you an idea of things like precision. You want small numbers whenever possible, but this could be a larger standard deviation either because of the way you measured it, you didn't take enough care in measurement, or because plant growth is affected by variables that aren't just water. Plants do what plants do. So, the amount of standard deviation, what is a good amount, varies depending entirely on what you're doing. But you're going to want that. And once again, you kind of have to have at least 3. You can technically do it with 2, but it's kind of a silly number with 2. You really want at least 3. Once again, more is always better. Okay, so I've got that, and I've taken my average, and then I'm going to go ahead, I'm going to do this for other amounts. That way I can get some change going on that I can look at. And then I'm going to tell Excel to plot this. And this is generally the way I like to do this one. Maybe not the perfect one. This gets it kind of cleaned up. You don't need all the lines that Excel does. You'll notice this doesn't have a chart title. This doesn't have a key on there. When I would take this and put this into, say, a Word file or a Publisher file or whatever I'm going to be creating my report with, then underneath it I would have a paragraph that would be kind of separate from the rest of the report that would say, figure 1 or figure whatever number this is. And there would be a short title about it and then any information that I would need there. So that would include my key. So what are the data points? Anything particularly relevant there that really needs to go with that. It doesn't actually go straight on the graph. It goes kind of adjacent to the graph in that figure caption. So then I've kind of cleaned it up. And you'll notice those standard deviations are back. That's what these little bars are. So if I go into the formatting one, I can set up error bars. And I have the Y ones. Typically we use Y error bars. We don't usually use the X error bars because, once again, you kind of, hopefully you measured right kind of thing because you controlled the independent. Although occasionally we do use X error bars, just not as commonly. But yeah, so you can control those guys over here. The way you actually put them in is you go into Chart Design, Add Element, and you just add whatever you need to add. The other one that, if I'm going to publish it, I'm probably not going to have that here, is this guy. This is the trend line. That's the line over, the line connecting the dots. And it's not really connecting the dots. You'll notice that the dots are sometimes going above or below the trend line, and that's perfectly normal. And what it's doing is doing a line of best fit. And you can choose what form of the line, if you want an exponential, linear, or logarithmic, etc. 99.99% of the time it's linear. And quite often the equation of that line, y equals mx plus b, is very, very helpful. Now, if I'm going to publish this, I'm probably not going to leave it on the chart, so I'm probably going to delete this. Likewise, R squared is a useful piece of information. This is basically describing how well that line does at fitting those data points. So if R squared was 1, it would basically be a perfect fit. Whereas if R squared was, say 0.7, it's barely a fit. Typically around an R squared of 0.3, which means about 30% of the data points are predicted via the independent variable. That's almost random. So, depending on what discipline you're dealing with, a lot of the social sciences, a lot of the life sciences, 0.7, 0.8, 0.9 would be acceptable. A lot of your hard sciences, you're looking at, 0.99999 being acceptable. And that would be saying that, 99.999% of the dependent variable is controlled by the independent variable. Basically, there's, a thousandth of a percent noise. Obviously, if you're dealing with humans or something, humans are messy. So you're going to be, much more tolerant of a larger R squared value. Now, I probably wouldn't actually put this in on the graph. So if I was going to publish this, I'd probably delete that, which you could just do by deleting, hit the delete key. Now, you can take your XY scatter plot and you can put 2 graphs onto it. So if you've got 2 things you want to compare them directly. So I can totally do that. I basically just tell them that I have 2 data sets. So you go to your graph, select data, and then you just add a new series. Now, once again, you don't have captions on this one. Those will go in the figure text. So you would say, figure 2, blah, blah, blah. And then I'd say, okay, the first series is this, maybe corn plants. And I would then insert the dot and then indicate that the dots represent the corn plants and the soybeans are with triangles. Now, I have done a couple of key features here. You always want to make sure that if you were to print it out in black and white, it would still be very much readable. This has two major reasons. One, it's still not uncommon for people to print these out, and black and white printing is cheaper than color printing. Basically, I get in trouble if I print way too much color. So if I'm going to print out a paper or something, it's going to go out in black and white. Now, I personally don't. I usually keep everything digital, but a lot of people do print. Second, this is an accessibility issue. If someone is colorblind, having a red and a green dot does not help them if they can't distinguish red and green because they're red-green colorblind. So you always want to make sure it's understandable in a black and white. And the way you do that is you select your series and you can change your marker. Where are you? You can change your marker style, and it's somewhere in here. Oh, here it is, marker options. And you can change what it looks like. You've got a whole bunch of different options. And then if you do insert symbol, you can find these same shapes and you can do that. Now, I've just done grays because, once again, typically these are going to be pretty much black and white, although now color is a lot more common. If I'm putting this on a poster, I'm going to go all out with the color. Don't go crazy, but, I'm definitely going to use color to my advantage. But you always want to change the shape. That way, someone who is totally colorblind is not going to be adversely affected by, trying to distinguish which color is which. Okay, now, the XY scatter plot is probably the most common, and there's variations of these, all kinds of, quirks to them. But these are going to be done when you have the independent variable is a value. It is a number, and it's not like an arbitrary number. So obviously, if it's rat 37, that 37 doesn't really tell you anything about the rat. That was just a cataloging number for the rat, so that wouldn't apply here. But if it's 1 milliliter, 5 milliliters, 20 seconds, that kind of stuff, something where that is a numerical value, and where on that line is really important because it's a it's a numerical value. Then you would put an XY scatter plot. We're assuming that the dependent variable, once again, is some kind of numerical output, some kind of measured value. So in this case, you've got two measured values. This is very common. Now, if you have instead the dependent variable is a measured value, whereas the independent variable is a lot more of not really measured value. So it might be something like comparing corn to soybeans to poplar trees or something, where the order doesn't really matter. These aren't like you measured the plant, and if the plant was a little bit different, it would be a soybean versus a corn. No, the plant is either a soybean or it's a corn kind of thing. So in this case, having a numerical value down there really doesn't tell you much. The idea of putting a trend line on here isn't that there is no X, in your equation. So you couldn't really do a trend line. Now, I will say there are some hybrids, like especially things like dates, putting months down there, where you can do kind of a hybrid between the two. But typically we will use bar graph, or Excel calls this a column graph, when really only the dependent variable is going to be a measured number. The independent variable might be something like with or without some kind of treatment, etc. And otherwise, it's done basically the same. We still have the error bars. The error bars are indicating the standard deviation. So the smaller the error bars, the smaller standard deviation. And this is really helpful because if my error bars are really big compared to the differences between my numbers, then that tells me that maybe I don't really believe that difference as much. Kind of the classic, if the error bars are overlapping, then all of a sudden it's like, is it these are meaningfully different, or is it just simply that this is the normal distribution, kind of the dumb luck of data? And so there's a lot of things get more interesting when the error bars overlap. And there are definitely things where you've got a true distinction where the standard deviations overlap a lot. So I'm not saying that's not true, but that is definitely kind of the next level of statistics. The baseline is, are the error bars nice and distinct? If the error bars are nice and distinct, like they are showing on this current graph, then you're like, okay, these differences are real. This looks legit. I should also point out, you don't have to start at 0, 0. In this particular case I have on both of these, Generally, you can get a little bit misleading if you don't start at 0, but sometimes 0 doesn't make sense. Like, if I'm measuring temperature for, days of the year, so I'm going to go, all 365, 366 days of the year, I'm not going to start at 0 Kelvin. That's silly. So you don't have to start at 0. If it's silly to start at 0, don't start at 0. And you can go negative. It can go down. I haven't done that in these couple, but you can. So that's perfectly legit as well. Once again, you want it nice, clean, polished, and in this case, you still have the figure text. Obviously, you're going to have your independent variable labeled a little bit differently. I've done A, B, C, D. That's just simply what I'm calling these things. You would probably call them, corn, soybeans, poplar trees, whatever they were. So this wouldn't just be so abstract and arbitrary. So if this was a real graph, it would be labeled with whatever it really was there. Sometimes you might have to get it in code or, shorthand of some sort just because it's too long to fit. But assuming it's not some weird thing where you have to use a big acronym because it's a really big word, you just put whatever these represent. Now, the one I see a lot, and a lot of people try and put it in there, and the one that in reality is almost never used is the pie chart. The only time you use a pie chart if you are representing effectively either percentages or the equivalent of percentages. You're looking at parts to the whole. So if I wanted to say, look at the distribution of gases in air, then I could do that. And I could do a nice pie chart, and most of it would be nitrogen, then it would be a wedge of oxygen, and then a few others. But if it's anything other than a percent composition of something, some kind of sample, what is my sample made up of? Pie chart's almost certainly the wrong one. And to be honest, I'm not entirely sure the best way to present a pie chart because they are so rare. Preparing for the video, I was like, okay, I'm going to grab a few science magazines I've got lying around, or science journals. They're kind of like on the border, and flip through the peer-reviewed articles in them. And I went through 3 months worth, I think three issues worth, and there was not a pie chart. These things are rare. I can probably count on 1 or 2 hands the number of pie charts I've seen while just normally reading through scientific articles. They are rare. So everyone loves the pie chart. It's almost never used in science. It can be used. There are definitely applications, but they're rare. So be careful if you're using a pie chart. As far as other fancy charts, once again, they occasionally are used. There's weird hybrids, but most of the time, usually you're going to be seeing some form of XY scatter plot or some kind of bar graph. Those are the dominant ones that we use. So I hope this is of assistance to you all. Have a wonderful day and enjoy graphing.